Hello, welcome to my actual chapter challenge about tennis, the worst sport in the world. Today we're going to be talking about some physics in the worst sport of the world. Last time we calculated our acceleration so we could use Newton's second law to calculate the force of one of the fastest serves in 2012. In order to find our acceleration, we used the formula velocity divided by time, which in this case was 73 meters a second divided by 0.32 seconds. This gives us our acceleration, which is 228.14 meters a second squared. Now that we know the acceleration of the ball, we can plug it into the formula with the mass of the tennis ball, which is 0.06 kilograms, and this leaves us with our answer of 13.6 newtons. With that background information, we can now move on to our next topic, which is kinetic energy, and how to calculate it in the worst sport in the world. So first, let's look at the formula for kinetic energy, which is 1/2 multiplied by the mass multiplied by the velocity squared. For the numbers in this equation, we can use the numbers from when we calculated the acceleration and force, which is 73 meters a second, which is our velocity and was used to calculate our acceleration, and our mass, which is 0.06 kilograms, which we used to calculate the force. So now, all we have to do is plug in these numbers into the equation, as seen on the screen, and so our final answer is 159.87 joules. Now that you've been enlightened and now know that there are 159.87 joules in one of the fastest tennis serves in 2012, let's step away from math a bit and look at Newton's first law. So as we can see here, Newton's first law states that if a body is at rest, or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless acted upon by another force. So an example of Newton's first law acting in tennis would be from this clip right here. So now, after watching that guy get obliterated, allow me to explain Newton's first law within tennis. Tennis is just making sure the ball bounces twice on the enemy's side, so you get the point. So if you don't act as the opposing force for the tennis ball, you're going to end up losing, which is something that you shouldn't be doing. So with that out of the way, let's talk about our next topic, which is going to be elastic potential energy. So before we talk about elastic potential energy, I would just like to ask you to not ask me questions about this part. This was the worst part to do. It was more tedious than video editing. It's so Also, please note that spring elastic energy is almost the same as string elastic energy, which is why it works in this equation. So with that out of the way, let's look at our equation for elastic potential energy. So what we need for this equation is a spring constant in Newton meters and the amount of bending in meters. So after a lot of complaining and screaming, I was finally able to get the numbers that I needed through some shady websites, which was great. So the spring constant I got from the shady website was K is equal to 453 Newton meters, and the bending amount that I decided on was 0.03 meters. So after plugging in the numbers as shown on screen, the answer that I got was 0.204 joules. This makes sense because string tension only makes up 2 to 3% of the actual power in the ball. This means that for some reason people who do the opposite of hating on tennis would do this. This section in tennis can also relate to Newton's third law, where every action in nature has an equal and opposite reaction. In tennis, when you hit the ball, the strings will bend inward towards you, while you yourself hit the ball away from yourself. It looks something like this. So now, rather than talk about the racket and the tennis ball, let's talk about the coefficient of sliding friction between the shoes and the ground. So first, let's get into the equation for the coefficient of sliding friction, which is force of friction divided by the normal force. Let's say we already know our force of friction, which is 10 newtons. Now, all we have to find is the normal force, which is found through this equation over here. Normal force is equal to mass times gravity. So going further, the average mass of a tennis shoe is about 1.13 kilograms. So now we plug those numbers in, as shown on screen, 1.13 multiplied by gravity, which is 9.8, and we get our answer, which is 11.074. So now we plug those numbers into the equation. 10 divided by 11 0.074 will give us our answer for the coefficient of sliding friction, which is 0.9. Sliding coefficient is relatively high because your shoes are made out of rubber, while the ground we assume is asphalt. Since we know that these two materials aren't known for being slippery at all, it makes sense why they would have a high sliding coefficient of friction. Well, that's it for me. Thanks for listening to my monotone voice again for over 5 minutes. And thank you for listening to me talk about the worst sport in the world for over 5 minutes.